In this video, we'll talk about partial fractions. Partial fractions describes the process of decomposing a single fraction into a sum of rational expressions. So we're going to take a fraction and break it up into fraction parts. Okay, and there are going to be some variables involved. So that here is kind of a summary. This is also in your textbook of the basic idea. And I think after we do one or two examples, this summary will make more sense to you. Okay, but I'm going to read through it at the beginning here anyway. So step one, I guess, is if we're working with an improper fraction. Improper means something where the numerator is larger than the denominator, right? And in this case with variables, we're going to look at the degree to decide that. So if the degree of the numerator, the top of the fraction, is bigger than it is in the bottom of the fraction, then we're going to divide the numerator by the denominator. We can either use synthetic division or polynomial division for that. And so we'll do one of those at the very end. Once we've done that, then we're going to complete the remaining steps using the remainder, which should now be a proper fraction, where the numerator is smaller in degree than the denominator. Okay, once we've done that, so the bottom of the fraction has a higher power, okay, then we can carry on with the rest of the steps. Step two, we're going to factor the denominator. Step three describes what happens if in the denominator I have a linear factor. So linear here means I have something where x is to the first power, right, or just x. It could be x plus a number, x minus a number. It could be, it's written here like ax plus b, right? It's linear. So if I have a linear factor in my denominator, then I'm going to break up this fraction into pieces. And so I'm going to write one of the pieces as a over that linear factor, which we're representing as ax plus b. This a is a constant that we're going to try and solve for. Okay, so if I have more than one linear factor, and maybe they're all different, then I'm going to have several of these added together, and I'm going to be solving for the coefficients in the top. Okay, if I have a linear factor that is repeated, then I'm going to include a fraction. Again, the top is a constant, the bottom is that linear factor. If it's repeated, let's say it's repeated 3 times, then I'm going to include the factor itself, the factor squared, and the factor cubed if it were repeated 3 times. Okay, most of ours are either going to be repeated once or repeated twice. So if it's once, then we just need the one fraction. If it's repeated twice, then we would need 2 fractions, one with just the factor and one with the factor squared, kind of giving us the opportunity to see it repeated. Again, I think that'll make more sense in a minute. All right, so step 3 is for linear factors. Step 4 is for quadratic factors. So quadratic factor here means that we have a factor with x squared in it. And the process is basically the same. So when I had a linear factor, I put a constant in the top, right? A linear factor has degree 1, it's x to the first power. And so we take the numerator to be 1 power less, which would be degree 0, which means that I don't have any x's, I just have the regular number or the constant. So it's 1 degree less. Same for a quadratic. So if I have for each quadratic factor, and something that's quadratic could have an x squared term, an x term, and a constant. So we kind of, this is just some generic quadratic factor. Okay, then I want to set up the numerator so that it's 1 degree less. So this would be degree 1, x to the first power, and I'm trying to solve for these constants b and c. Okay, and then the same thing's true if the factor is repeated, then I'm going to include that many fractions until I get up to how many repetitions I have. So again, if it were repeated 3 times, I'm just using that as an example, I would include one fraction where that factor was represented once, one fraction where the factor was represented twice as a square, and then if it were 3 times, I'd also have a fraction where it was repeated 3 times, and I'd see it as a cube. Okay, so we're going to set these up. We're going to use the capital letters as our variables. You don't have to use the subscripts if you don't want to. I don't generally like the subscripts, but I just wanted to be consistent with what's in the book. And then we're going to use algebra to solve for A, B, and C. This is why this is in this chapter, because we're going to need to solve a system of equations to figure out the final answer. Okay, I may come back to this, but let's try it out. All right, so here's one from your book. I went ahead and factored the denominator for us. But if I had not done so, let me just put that up here in the corner. Notice that the degree of the bottom is higher, which makes this a proper fraction. So I don't have to do any division. I can just start right away with factoring the denominator, which I've already done. Notice my 2 factors, x and x plus 1, are both linear. So let's go back to this real quick. For each linear factor, I'm going to include a term where I have a constant over that factor. Okay, so for the linear factor x, I'm going to include the fraction a over x. For the linear factor x plus 1, I'm going to include the fraction, I'm going to use b this time so that they're different, b over x plus 1, right? Neither of these is repeated, so I don't have to worry about that. Neither of these is quadratic. I don't see an x squared here, so I don't have to worry about that. Okay, so that's the basic setup. From there, I want to work with the right-hand side to rewrite it as a single fraction with my variables a and b, and then once I've once I've written it as a single fraction, I'm going to set the numerators equal to each other, and that's going to allow me to solve for a and b. Okay, so first we want to get a common denominator. So since these don't really have anything in common, I can't really separate the x here from the plus 1, so they don't share any factors. I'm just going to multiply the 2 of them together. Okay, so this is me getting a common denominator. To do that, I'm going to multiply this first fraction by x plus 1 on the top and the bottom. And I'm going to multiply the second fraction by x on the top and the bottom. So I'm going to have a times x plus 1 over the common denominator, and I'm going to have b times x. Now that I have it with the same denominator, I can write it as a single fraction. And I'm going to go ahead and distribute the a. So I'll have ax plus a plus bx. Okay, so here I'm going to write it as a single fraction. Okay, now my goal is to make this be comparable to this. So I want to collect all the like terms. So for the ax and bx, I have ax plus bx, those both have an x, and I have the a. Okay, so I'm collecting like terms. All right, now I'm going to factor out the x. I'm going to put it in the back so that I have a plus b times x plus a Okay, now let me bring this fraction down here so that we can see them side by side. So these are equal to each other. So if that's true, then the coefficients for x must be equal. So this implies that a plus b must be equal to 3. And the constants must be equal. So that implies that a must be equal to -1. Our goal really is to solve for a and solve for b. So we've already got a. It was pretty much given to us. So now let's take what we have for a and plug it in to solve for b. So that means -1 plus b equals 3. So if I add this 1 over, b must be 4. Okay, so to write it neatly, okay, I don't always get to write it neatly, but I will try to do it this time. Here's our original fraction, right? The whole goal is to take this fraction and break it into partial fractions, right? Two fractions that add to be this fraction. All right, so I'm going to go all the way back to the top. Before I got a common denominator, I had a over x and b over x plus 1. So now I want to put in the numbers I have. So I have a is -1 over x plus b is 4 over x plus 1. Okay, so really this right here is my final answer. Okay, so it does bring in some of our fraction skills. The gist of each problem is the same, and the basic steps are the same. So I think once you've practiced a couple, I think you'll be more comfortable with the process. The initial setup is important, so we do have to kind of reference that first page that we looked at together to help us get the initial setup. All right, let's try another one. Okay, actually this one is also factored for us. Aren't you lucky? Okay. I'm not going to FOIL this out because that would take some effort that I'm not sure would totally be worth it. But if we did FOIL it out, what would be the degree? It would be x, in the very front, it would be x to what power? X squared squared would be x to the 4th times this x out front would be x to the 5th, right? So I'm not going to multiply it all out, but if I did, it would be x to the 5th plus some other stuff. In the top, we have x to the 4th. So this is proper, right? The denominator has a higher exponent, which means we don't have to do that synthetic division. We don't have, or whatever kind of division we need to do. We don't have to do it here, right? It's proper. Okay, so now we can go to step 2, which would be to factor the denominator. That's already been done for us. So then we want to set up our fractions. Okay, we have one factor and then a second factor that's repeated. So the first factor is linear, so that's going to look just like the last problem. The second factor is quadratic and it's repeated. So let's take a look back. For each quadratic factor, we need to include a term that looks like this. So we'll have our quadratic factor in the bottom, and we'll have a linear factor on top. So like bx plus c. Okay, and since it's repeated, we're going to have one with our quadratic factor and one with that same factor squared. So let's do that. So x squared plus 1, that's our quadratic factor. Because of the x squared, we need to make this linear, which means we need an x. And we need two more variables. Okay, because it's repeated twice, we also need a factor that includes x squared plus 1 squared in the denominator. And we're going to use different variables. I don't like the subscript, so I'm just going to use dx plus e. But if you would rather use b1 and b2 and c1 and c2, you're welcome to do that. Okay, from here, now that we have this set up, right, the steps are the same. We want to get a common denominator, write this as a single fraction, and then collect all the like terms. Okay, so I'm going to stretch over here because I think this is going to be a little long. So this is going to be our common denominator. So anything we're missing, we need to multiply top and bottom by. Right? So in this first fraction, I have the x, but I'm missing x squared plus 1 squared. So I need to multiply by that on the top and on the bottom. Okay, for the second fraction, again, I want the denominator to look like this. So what I'm missing 1x and 1x squared plus 1. So I need to multiply by that on the top and on the bottom. So bx plus c times x squared plus 1. Okay, and then last one, this time I'm only missing the x. So I'm going to multiply dx plus e times x Okay, so that same first step, I got a common denominator. Now I want to write this as a single fraction, and I want to expand all of this at the top here, right? So we'll try and do some of that at the same time. Why don't we FOIL this first? Let me jot it down above here. So this is the same as x squared plus 1 times x squared plus 1. So that's going to be, I'm going to leave the a out front for the moment. So that's going to be x to the 4th plus 2x squared with my outside and my inside added up plus 1. Okay, and then I don't know if we're going to be able to do all this at once, so we'll do it in 2 steps. We'll leave this bx plus c for right now. And we'll make this x cubed plus x. How about that? We'll FOIL that next. And then I can multiply this by x, so this will be dx squared plus ex all over our common denominator. Okay, so this is going to be ax to the 4th plus 2ax squared plus a plus, now let's FOIL these two together. This will be bx to the 4th. On the outside, we'll have plus bx squared. On the inside, we'll have plus cx cubed. And then at the last, cx. We also have dx squared plus ex. Okay, so we've expanded it completely. Now we want to collect all of the like terms. So we're going to start with the highest power of x, which is x to the fourth. So I have ax to the fourth and bx to the fourth. I'm going to go ahead and factor out the x to the fourth just to save ourselves a step. Okay, and then I have cx cubed. Now I'm looking for x squared. I have 2a, I have a b and a d. And then x to the first, I have a cx and an ex. And then constants, just a. All right. So now I want to set this equal to the original. Let's see if I can squeeze that on here. In the original, I started with x to the fourth plus 1 in the numerator. Okay, which means this is a 1 in front of the x to the fourth. We'll have lots of missing terms in between, right? 0x cubed, 0x squared, 0x, and then the constant is 1. So let's jot down all those equations. So we have a plus b equals 1. That's because the coefficient for x to the fourth is a 1 over here. That's where that's coming from, right? I don't have an x cubed here, so c must be 0. I don't have an x squared term, so 2a plus b plus d must be 0. I also don't have an x to the first term, so c plus e must be 0. And then a is the constant term, which is 1. Okay, so a lot of this solving has actually already been done for us. Let's see if we can write down what we know. So a must be 1. A plus b equals 1. The only way that can happen is if b is 0. C is 0. Let's see. Let's plug this one in off to the side. So 2 times 1 plus 0 plus d equals 0. So that's 2 plus d equals 0. So it looks like d must be -2. Okay, and then c is 0, and c plus e is 0. So e must also be 0. All right, so we're going to take these numbers, we're going to go all the way back to the top, and we're going to fill them in, right? A is 1, B is 0, C is 0, D is -2, and E is 0. All right, notice that B is 0 and C is 0. So really this whole fraction, we don't need it, right? Because we have 0 over the denominator, that's just 0. All right, so I'm going to write our final answer. This is why it's so hard to write it neatly, because these are kind of long. Here's our original fraction. Okay, a was 1, so that means 1 over x. Like we just said, since b and c are both 0, that second fraction we don't really need. And then the only other non-zero number we have is -2 for d. So it would be -2x plus 0, which is just -2x, over x squared plus 1 squared. So this right here is the partial fraction decomposition. Looks like that. All right. So I'm definitely not doing all the possible problem combinations out there, but I hope that these two, and we're going to do one more, give you a really good idea for the process. So what that means is you're going to have to go in and do, you know, a couple practice problems, as many as you can really, so that you can be ready for any kind of scenario that you find. Let's try one more. Okay, so here's the one where the degrees are equal. We don't have a proper fraction. This is an improper fraction. So before we can do the problem, we need to divide. Okay, and because we're not dividing by something that's x to the first, we can't use synthetic division, unfortunately. We have to use long division. Long division looks a lot like traditional division with numbers, and it operates a lot like synthetic division. So we want to think, all right, x cubed goes into x cubed. One time. I think we're going to put that 1. I've kind of forgotten. I think we're going to put that 1 right here, aren't we? No, we're going to put it right here, but we're not multiplying by x. I guess we're going to put it right here. Oh, because this is plus 0. Okay, so then 1 times x cubed. We're just multiplying everything by 1, so we're going to copy it down. Plus 2x. And there's no constant, so we're going to add a plus 0 so that the lengths match. Okay, and then just like normal division, we're going to subtract. And the x cubes are going to divide out. 0 minus -3 is going to give us a positive 3x squared. It's like a double negative becomes a plus. 0 minus 2 is going to be a negative 2x. And then 2 minus 0. Okay, so technically that division, I'm going to write it here, is going to give us a 1 plus a remainder. Remember, this remainder did not get divided yet, so it's still in a fraction. 3x squared minus 2x plus 2 over, what is this, the divisor? X cubed minus 3x squared plus 2x. Okay, so we are going to do partial fractions on this. Okay, so let's write that down here. Actually, maybe we can write our final answer right here. So when we write our final answer, we'll have the 1, okay? And then we're going to break this into parts. So we have 3x squared minus 2x plus 2 over, we really like to factor the denominator. I'm struggling to get it all on the screen here, but notice all 3 parts have an x, so I'm going to go ahead and start that process and factor out an x. That's going to leave us with x squared minus 3x plus 2. Okay, I'm going to go ahead and move this up. I hope that's okay. I'll do this. Okay, and then this can be factored. So that's going to be two and 1 and 2 minuses. Okay, so notice now that it's all factored, we have 3 different linear factors. That's good. That means this part should not be too complicated, right? Remember, for each linear factor, we want a fraction with a constant on top. So just the variable, like a or b or c. Okay, so now we're going to go through the steps just like we did in the past. The only difference for this problem was that first step to make it a proper fraction. Okay, so we'd like to have a common denominator. Just like before, these 3 don't really have anything in common, so we would really like to write it with all 3. So anything that's missing, we would need to multiply it by. So we're going to multiply a by x minus 1 and x minus 2. For the middle fraction, we're going to multiply the b by x and x minus 2. And for the third fraction, we're going to multiply the c by x and x minus 1. All right, so now, just like we've done in the past, we want to write these together as one fraction. And we want to expand all the numerators as much as we can. So let's do that next. All right, I'm going to leave the a out front and do this in 2 steps like we've done in the past. So we'll FOIL these together. This will be ax squared minus 2 minus 1. So minus 3x plus 2. This will be b times x squared minus 2x. And this will be c times x squared minus x. Okay, so now let's go ahead and distribute the a, b, and c. So we'll have ax squared minus 3ax plus 2a plus bx squared minus 2bx plus cx squared minus cx. Okay, now we want to combine like terms. So let's see, all the x squareds. Right? We have an a, a b, and a c. And then all the x terms, we have a negative 3a, a negative 2b, and a negative c. And then all the constants, which is just the 2a. All right, so now we want to go back to the original. All right, not all the way back to the top, but after we did our division. I'm going to squeeze it over here. So we had 3x squared minus 2x plus 2 over our denominator. Okay, so now we want to set all the coefficients equal to one another. So that gives us a plus b plus c must equal 3. Negative 3a minus 2b minus c must equal negative 2. And 2a must equal 2. Okay, so this is a system of equations, right, that we need to solve. I think the first thing that we can solve for here is a. So we know that a is 1. Maybe it might be easier to go ahead and plug that into both of these, and we can solve them from there. So that's going to lead us to, if a is 1, this will be 1 plus b plus c equals 3. But we could subtract the 1 over. And if we subtract the 1 over, we'll have b plus c equals 2. And then for this one, if we put in a to be 1, we'll have negative 3 times 1, which is negative 3, minus 2b minus c equals negative 2. And if we add the 3 over to the other side, that's going to give us negative 2b minus c equals 1. Okay, so let's put these two together, right? And I think we can probably solve by elimination. The c's already have coefficients that are equal but opposite, so we could add these together. And the c's will add to 0, so we're going to get negative 1b equals 3. So if I divide by negative 1, that means b will be negative 3. Okay, and then maybe we could go back to here, right, to get c. So negative 3 plus c equals 2. If I add the 3 over, c must be 5. So at the very top, I won't scroll down because I can't fit it all, but I have a is 1. Right, that led to getting b, which led to getting c. Okay, so here's our initial problem. right? We did the division and we divided it out. We got an extra 1. And then we broke it up into 3 fractions. Bring that up right here. So we're going to put in the value for A, for B, and for C. So we've got A is 1, so this is plus 1 over x. B is negative 3. So I'll put the negative 3 in the top of the fraction, but you could have done minus 3 over x minus 1. That would be the same. Plus 5 over x minus 2. So this right here is our final answer. All right, well, I hope that gave you at least a little bit of a start to begin thinking about how to decompose something into partial fractions, how to do all this fraction work to kind of break it into pieces. This is useful in calculus for derivatives, and I think maybe more so integrals. So this is why we're practicing, right? All this manipulating fractions. So good luck with this. Take some time to study it, and we'll see you in the next video.